To op-amp comparators, theory and operation. I'm your host, Louis Laughlin. Please visit my website at www.bristolwatch.com. In this video, we are going to study comparators. These are very important circuits that's used in microcontroller, modern microcontrollers, and other forms of digital and analog logic. First, let us ask, what is a comparator? What is a comparator? A comparator is an op-amp with no feedback. And its most important use is it connects the digital world with the analog world. While it is certainly an analog circuit, with its proper use, we can use comparators to read the analog world and send the information to our digital world, such as microcontrollers. It's also at the heart of things like analog to digital conversion, as we will discuss a little later. First, before we move on, let's watch a short video of two actual comparator circuits in operation. All right, what we're looking at here is two different comparator circuits. On my left here is a 741 op-amp. This is connected as a bipolar, that is, it has a plus and minus power supply. And on the right is an LM358, which is a unipolar device. Both are operating at 12 volts. And what we're going to look at here is how they operate. Without comparators, we could never connect the digital world to the analog world. They're the basis of analog to digital conversion and several other ideas that we use every day in microcontrollers and electronics. A comparator, as the name sort of suggests, compares two input voltages. A comparator being nothing more than a operational amplifier with no feedback. If one voltage exceeds the other, it switches all the way on. Looking at the LED on the right, this is a potentiometer. I'll show you the schematics to both these circuits after this video, and we'll discuss them more closely. Look at your readout here. Over here is about a 6 volt Zener diode, if you can see it. So that's going to be my reference voltage for the 741 op-amp. And if the voltage going on what I call VN in the schematic, voltage in, exceeds a certain value, you notice the LED comes on. If I go below that value, it turns off. Again, if we go above that value all the way to 12 volts, it doesn't matter. It's on once it's past that reference value. Off and on. Alright, I had to cut the overhead light down for this next part of the experiment, but it will become obvious why I did this. If we look on the right side of the page, there is my LM358 op-amp. But over here is a cadmium sulfide photocell, or what they call photoresistor, with another resistor in series. This time I'm using the one of the inputs on the op-amp to come from this photocell resistor combination. And depending on where I adjust this pot, if I block the light from the photocell, you notice the LED is coming on. The idea of this being, you notice, is it's off and on, and I can change the sensitivity by changing the reference voltage. You notice it's now much more sensitive since I adjusted the reference voltage. This enables a microcontroller or digital logic to sense analog events such as temperature, light intensity, and so forth. This is also the basis of analog to digital conversion, which I used in another project. We will go over the schematics of both these particular op-amp circuits in the following slides when I explain them more closely. Let's look a little closer to the electronic side of the comparator circuits that you saw in the video, part of this presentation. Here we have an op-amp A. You notice it has a plus input and a minus input. Here we have a voltage divider that produces what we call V reference. In this case, it's 1/2 VCC, whatever it happens to be, just for illustration's sake. And that is connected to the minus input. Over here, the voltage waveform is going to be put in on Vn, which is going to be on the plus input. This is called a non-inverting comparator. Look over here to your right with the waveform. VC, the red line, of course, is Vref. That is what's on the minus terminal of the op-amp. And on the plus terminal, we have this triangular wave. As the triangular wave moves up and is equal to V reference, the output will switch high. And as long as Vn is greater than V reference, the output will remain high, and when it drops below V reference, it will go low. So this way, if we had an output, say it was 5 volts, an Arduino or a microchip PIC or any other form of logic would know, hey, the voltage went above a certain point. There's also a lot of analog circuit uses, but this is going to be more oriented towards digital. Note that when this op-amp turns on, it's either all the way on or all the way off. It should not be anywhere in between. Thus, it would form a square wave. Now, if you're using something like an LM358 op-amp, which will operate at 5 volts, this is an easy direct interface to a microcontroller. Now we're going to change things around just a bit. We have the same op-amp as before, but you notice something different. We have connected V reference, which again is going to be 1/2 VCC through this voltage divider, to the plus input, and our signal input is Vn is going to be on the minus input. This is what is called an inverting comparator, and it does the exact opposite, uses the same part, just move the plus and minus terminals around. It does the same thing, but in the inverse direction. Looking over here right on the waveform again. Here is V reference, and you notice as long as Vn is less than V reference, it is high out. When Vn exceeds V reference being the positive terminal this time, the output will go low, and so forth. So, okay, it does the opposite from what the non-inverting input does. Well, we can utilize this in something we will study in a later video on window comparators. What we're looking at here, this was taken directly off of a specification sheet for a microchip PIC 16F628. Many microcontrollers, including the heart of the Arduino, have built-in comparator circuits that by setting the appropriate bits in the microcontroller, you can access them. In the case of the PIC 16F628, it has 2 of them that have a number of differing configurations that enable you to do all kinds of incredible stuff. Well, let's look again at this. If you notice in the illustration here, we're inputting a sine wave, and this is the result. We have fixed Vn negative, which is we're using it here as a reference. And once again, Vn on the plus terminal, as it exceeds Vn on the negative terminal, we will get a high output. So that gives you a little more illustration. This is built right into many of your modern, more complex microcontrollers. They have built-in comparator circuits. All right, here's a comparator that's been constructed with an LM741 operational amplifier. This is the exact circuit that you saw in operation in the video. Again, we have used the minus input as a reference, but this time I have used a Zener diode and a dropping resistor as opposed to two resistors as a divider. This you want to do in quite a lot of circuits, because if you were to change the voltage up here at plus 12 volts, if it was to drift around, your V reference would drift around and it could cause you some problems. In this case, I have Vn going to the plus terminal from a 10K potentiometer. As you notice, when I adjusted the potentiometer, when Vn is equal to or greater than V reference, the LED turned on. Notice that this is a bipolar device. It uses plus 12 and minus 12. In deference to that, I had to insert a 1N 4001 silicon diode, or you can use a 1N 914, anything like that, because this thing doesn't switch from 12 volts to 0. It switches from plus 12 to minus 12. And it would have really reversed the biased the diode LED and could have damaged it. So that's what this is for. So as far as that goes, like I said, Vn exceeds V reference, LED will cut on. But it's a real headache with these bipolar devices, because a lot of times you don't have a minus 12 volt supply hanging around. Let's look at how to get around that problem. All right, this circuit here does the exact same thing as the LM741 circuit we saw earlier. But now we're using an LM358 op-amp, and these are unipolar devices, or they can be operated as unipolar. That's what they're designed for. So we get away from the problem of having to have a negative supply, and the output, and when Vn exceeds Vref here, is going to go to near 12 volts and is going to light the LED. When it's off, it's near 0. So, a little simpler, no bipolar supplies to put up with, and this LM358 will work down to 5 volts, which could make it easier to connect to a microcontroller. But we can do a little bit better than this. Now we're going to come to the LM311. This is designed as a comparator. It's not an op-amp any longer. It is an actual comparator. But what is really nice about this is the output is what is called open collector. It has a transistor that's open collector that I have to connect a pull-up resistor to a power supply. There's a little bit different things we have to look at in these, which I will cover in a video on the LM339 comparators. But for now, the way this is normally set up, Vref, I just happen to use a resistor divider this time, is always going to be set for the plus input. This is largely designed that if the Vn on the minus input is greater than the Vref on the plus input, the output will switch low. The transistor turns on, and it's like a switch to ground. The voltage out here goes to near 0. Not a whole lot to it, but you notice something different here. I could operate the LM311 at 12 volts, but by using an open collector output, I can pull that to 5 volts. Direct interface to a microcontroller. So I can operate 12 volt, I can read 12 volt sensors out here, have a direct, easy connection to a microcontroller. In fact, I utilize this in one of my other videos. Here is the schematic to my Arduino DAC-based voltmeter project that was presented on another web page in a video. How does this work? Well, here is our friend, the LM311 that you just saw. I pulled the open collector output to 5 volts, and I connected that connection back to digital pin 4. What did this do? Okay, digital pin 11 was set up in order to utilize its pulse width modulation output, which through this filter gave us a voltage from 0 to about 5 volts. This LM358 is used as a voltage amplifier, not a comparator, which feeds to the plus input of the LM311. And so what we're doing, if I have a voltage in, maybe I'm reading whatever voltage I have here, all I have to do is step through is to vary the voltage coming out of the LM358 Arduino combination. Sooner or later, it's going to switch either high or low, pin 7, and when it detects the pin 7, back through digital pin 4, that is pin 7 on the LM311 state change, is read on digital pin 4, the Arduino automatically knows, hey, this count gave me this voltage, and you multiply it by whatever it was, and you can get a voltage reading. This is the basis of an analog to digital converter. That's what this is. It's an analog to digital converter. I set this up to work up to 24 volts if necessary, as opposed to the 5 volt limit that you have in the Arduino itself. This is a partial snapshot of the internal workings of your Arduino microcontroller, that is, the ATmega 168 microcontroller in this case. What do we have here? This is how your digital analog to digital conversion works. All right, what do we have here? We have an analog multiplexer. Here's your analog to digital inputs, wherever they are. It's fed to VN, there you go, sample and hold comparator. Whatever the voltage is there. Now what you have is conversion logic. It's some kind of resistor ladder network probably. And you have what is called a 10-bit DAC, digital to analog converter. So this puts out a voltage which I labeled Vref. I could have just reversed them, but I generally use the voltages I'm measuring as VN. It varies the output voltage on the DAC, and it looks for the relationship somewhere that the output state change on the comparator is going to signal the conversion logic, hey, I have a match. It depends on how it works. There's different ways that these could work. But basically, if Vref is greater than Vn, it probably does some kind of logic change. And the number that you get back when you do an analog read, say 0, is that 10-bit number from 0 to 1023. So that's how your analog to digital converters work. Finally, here is a sample useful comparator circuit that you could use as an overvoltage indicator. All right, I'm using the LM311. I'm utilizing its open collector output. When switched on, will light up an LED. I have set V reference. I have fixed it with a Zener diode as I had done in an earlier circuit. And here I have an adjustment. and I will adjust the 10K pot here to where the LED just turns off. Now, if something was to happen, let's talk about a car charging system. You know that those things are supposed to run no more than, oh, I don't know. When it's charging up, it's 13.6 to 14.5 or something. You could connect this as a overvoltage indicator if something fails, and sometimes these charging systems will fail. The regulator will short through, and you could be charging 15 to 18 volts. And you probably wouldn't notice it until your battery's destroyed or your electronics is messed up. But if you had the car idling and you plug this thing into the lighter and adjusted it where you know the voltage is normal when it's running, if the voltage exceeds and you'll adjust it where the LED is just off, if the voltage exceeds a certain level, it'll give you an indication something is up. You can use a series of these with the appropriate voltage dividers to provide a crude voltage indicator, which we will look at in another video. But for right now, basic overvoltage indicator. So I hope you enjoyed this introductory tutorial. We got more coming as we look more and more into comparator circuits. I'm your host, Lewis Laughlin. Visit my website at www.bristolwatch.com.